Hi guys, Dr. Burns here. We're going to take a look at section 3.9 and we're getting into some derivative rules for logs and exponential functions. We haven't done a lot with logs and exponents this semester, but I want to just remind you of a few things you would have learned in pre-calculus with regard to expanding and condensing logarithms. So a few rules here that, again, I think you saw these in pre-calc, but I want to refresh your memory on these. If you take the log, so let's back up. Remember, the log is written as log base b of some argument. So anytime you see log, there's always a base of some kind, and then there's some sort of an argument. They may or may not put parentheses there, but just like when we deal with trig functions, what's here is that argument, so it's not multiplication or anything like that. And there's two more common logs that we see very often. If we see log log with nothing written after it, that's an implied base 10. That's called the common log. That's the name for it. And then there's also the natural log, which is very common. That's ln, and that would be equivalent to log base e of whatever the argument is, but we usually just write ln. So those are the ones that come up. That's called the natural log. Those are the ones that come up most often. So a few rules associated with these logarithms. Log of 1 is always going to be equal to 0. And the reason that works is because you may remember that if you have log... Hi everyone, Professor Burns here. And I want to take a look at section 3.9, which gets into some derivative rules for logs and exponential functions. We haven't done a lot with those this semester, but hopefully you saw those in pre-calculus. And I want to just refresh your memory on a few things before we get into the derivative rules. So logs and exponential functions are a special sort of branch of functions. They go hand in hand. The definition, if you have an exponential function, say you have b to the x, and we know that that's equal to y, you may remember that that could be converted to a log by writing it as log base b of y, and that's equal to x. And those go back and forth. So we could always convert between log and exponential functions using this definition. They're inverses of each other. That's the relationship they have. And so when we work with logs, there's several properties here that we can use to expand and condense logs. First property is log base b of 1. So b is the base, doesn't matter what the base is. Log of 1, if the argument is 1, that's always going to be 0. And think about from this definition why that works. Well, the definition in exponential form says that this would be b raised to the 0 power. Well, anything to the 0 power we know is 1. So the log of 1, regardless of the base, is always going to be equal to 0. If we are multiplying two things in the argument, we can expand it. If there's a log in front of it, we can expand it as the addition log base b of m plus log base b of n. And that's going to make the derivative a little easier to take, and we'll see that in a second. Same thing with division. If we're dividing m divided by n in the argument, we can expand that as log base b of m minus log base b of n. And then finally, this power rule says if we have log base b of m raised to a power, we can bring that power to the front and write that as p times the log base b of m. And again, that's going to make the derivative a little easier to figure out. So let's practice expanding some logarithms using these properties. Letter A here, it says the natural log. And by the way, what is the natural log? The natural log is a log that's basically base e. We just don't write it that way, but that's really what that is. So we usually just write ln to represent the natural log. Another one that comes up a lot, if we just see log of x, that is the common log, that's base 10. So those are two that you'll see from time to time. I would say natural log is probably the most common, and we'll come back to that one a little bit more in a few minutes. But let's look at this expansion problem. So it's the natural log again of the square root of 3x plus 2. So just like always, when you see a radical, I want you to think I have to write that as an exponent. Since this is the square root of 3x plus 1 to the first power, we can write this as the natural log of 3x, I'm sorry, I said 3x plus 1, 3x plus 2 rather, to the first power. We can write this as natural log of 3x plus 2 all to the 1/2 power. And then using property number 4 here, the power rule, we can bring that 1/2 to the front. So this becomes the natural log of 1/2 times the natural log of 3x plus 2, and just make sure you leave that in parentheses. 3x plus 2, I'm adding everything in the argument there. There's nothing else I can do to expand that. So this is as simplified as this gets. Letter B, same thing. We want to expand this logarithm. And the first thing I hope you notice is there is a radical. So let's take care of that. That would be the natural log of x squared plus 3 to the second over x to the, I think that's x to the third, and then a square root again, I think is what I intended there. So that becomes x squared plus 1 to the 1/2 power. And then you see that I'm dividing the argument. So let's go ahead and apply property number 3 and separate it into subtraction. So this will be the natural log of x squared plus 3 to the second minus the natural log of x cubed times x squared plus 1 to the 1/2. And then because I'm multiplying what's in the argument in the second log, like all of this is the argument for that logarithm there, I can make that addition. So we end up with, and by the way, this 2 is an exponent, so that can move to the front of that log. So we can write this as 2 times the natural log of x squared plus 3 minus the natural log of x cubed, and then it's addition here because it's plus, because there's multiplication there. So natural log of x squared plus 1 to the 1/2, but you have to be careful because of this minus sign that has to apply to both of those logs. And I didn't leave enough room here, my apologies, but that will give us, that negative can get distributed. And then also notice now that you've got an exponent here and an exponent here. Those can move to the front of their respective logs. So let me come down here and write, we end up with 2 times the natural log of x squared plus 3 minus 3 times the natural log of x minus 1/2 times the natural log of x squared plus 1. And I think that's as far as we can go with all of that. And the reason this is useful is because when we take derivatives, it's much easier to take the derivative in expanded form of the logarithm than having everything jumbled up. Otherwise, we're doing quotient rules and product rules and chain rules and all kinds of crazy stuff. The derivative will be much easier to work with after we've fully expanded the log, and that's what we're going to practice in this lesson. So before we start doing some derivatives, let's make sure we understand the rules. So make sure you put a little star by this. When we see a logarithm, the derivative of log base b of x is going to be written as 1 over the natural log of b times x, whatever is in that argument. So that's the rule for taking the derivative of a logarithm. And then if we have an exponential function, the derivative d dx of a to the x, a is the base this time, that's going to be the natural log of a times a to the x. I don't know why I used a instead of b. Same thing though, it's the base, just the base for the exponential function. And you don't have to have these memorized. I think I would give you these formulas if you needed them on a test, but make sure we see how to use them. So let's do a few examples here. Start with letter A. So first of all, this is an exponential function, y equals 2 to the 3x. Notice that the base is 2, and notice that it's to the 3x power and not just x. So because there's anything other than just a regular old x here, I have to use a chain rule. So this is a chain rule where the inner function is going to be 3x and the outer function is going to be 2 to the x. So I'm going to apply this new rule I have here for taking the derivative. So it's going to be, I'm going to call it y prime equals the natural log of 2, you just leave it like that, times 2, so it's the derivative of the outer, but evaluated at the inner, so evaluated at 3x, times the derivative of the inner, which is the derivative of 3x, which is just 3. And you can leave the answer just like that. If you want to clean that up just a little bit, you can put the 2, or the 3 rather, maybe in front and write it as the 3 times the natural log of 2 times 2 to the 3x. And I think that would be sufficient. And that's really all that we can do with that. Let's take a look. I'm going to skip down to letter C because that's another exponential function. So the base this time is e. Notice it's to the 6x. A lot of times these are going to be a chain rule. So the inner is going to be 6x. The outer is going to be e to the x. So my derivative is going to be the natural log of e times e to the 6x, and then times the derivative of the inner, which is just 6. And the natural log of e, that's another log property you may or may not remember, but the natural log of e is always going to simplify to just 1. If you put it in your calculator, you'll see what I'm talking about. But if you forget and you just leave natural log of e, that's okay too. So I'm going to clean this up a little bit and write it as 6 times e to the 6x. And that would be my simplified answer. Now let's get over to letter B. We're looking at a log function. Notice there is a radical. Always fully expand. If you have a log, see if there's anything that can be expanded using those properties earlier, let's do that. So I'm going to write this as the natural log of 4x minus 2 to the 1/2 power. And then I'm going to bring that 1/2 to the front. So this is 1/2 natural log of 4x plus 2. No calculus yet, no derivative yet. This is all algebra. Now this is fully expanded. Let's apply the rule for finding the derivative. So the derivative says the 1/2 is a constant multiple, so it's going to be the derivative. It's another chain rule here. The inner function is 4x minus 2. The outer is the natural log. So the derivative of the outer, I'm using this formula, it's going to be 1 over natural log of the base, because it's the natural log, the base would be e, and then evaluated at the inner function, so evaluated at 4x minus 2, times the derivative of the inner function, which is just 4. So clean that up slightly, I get 4 over 2 times the natural log of e, remember, is just 1, so that's going to just go to 1. And I'm just left with 4x minus 2 in the denominator. And of course we could reduce that, but I'm not worried about it right now. I'm just going to leave my answer like that. Last one, letter D, we've got log of cosine of x. Remember, if it's log with no base written after it, that's a common log of base 10. So my base is 10. Nothing to expand there. It's just log of cosine, and that's it. So my derivative, I'm going to go ahead and apply the derivative rule. I have to use a chain rule again. My outer function is the log. My inner function is cosine. So the derivative of the outer, it's going to be 1. Again, make sure you see I'm using this rule right up here. 1 over the natural log of the base, which is 10. So 1 over the natural log of 10 times x, evaluated at the inner function, since it's a chain rule, which is cosine, times the derivative of the inner function, which is negative sine. And if we want to clean that up slightly, we can write it as negative sine x over the natural log of 10 times cosine x. That is negative tangent if you want to simplify it, but of course you certainly do not have to use that trig identity. You can just stop and leave your answer just like that. I think that is all I want to go over right here. I just want to give you a few examples, but we will do some practice applying these derivative rules in class. And like I said, you don't have to have these memorized, but most of them will involve a chain rule of some kind. So we'll do some practice with those, and I'll see you tomorrow in class.